Good morning, good afternoon, good evening. Whatever time you're watching this, I hope you're doing well. Thank you for being here. Our presentation today is titled Impacts of Climate Change, the Atlantic Meridional Overturning Circulation, or AMOC for short. I'm Braden Ansaldi, and I'm joined by Cameron Class and Charles Hammond. Together, we will guide you through the science behind AMOC, what causes changes in it, and why it matters globally. Our goal is to help you understand a key system that controls climate patterns and to show how climate change is disrupting this balance. We'll also explore scientific case studies, scientific models, and what actions we can take moving forward. Let's dive in.
What is the AMOC? The AMOC is one of the planet's most powerful ocean circulation systems. Imagine a giant conveyor belt moving heat and salt around the Atlantic Ocean. Warm, salty water travels northward near the surface, then cools, becomes denser, and sinks in the North Atlantic before flowing back south at deeper ocean levels. This circulation is powered by thermohaline processes. That means it's driven by temperature and salinity differences. These factors affect water density, which in turn drives this massive movement. Why does this matter? Because the AMOC helps regulate climate across the globe, especially in Europe and North America. For example, without the AMOC, much of the Western Europe would be significantly colder. This system also affects the distribution of rainfall in the tropics and plays a crucial role in the carbon cycle by storing carbon dioxide in the deep ocean. So, disruptions to it could have massive global consequences. The diagram here shows the path of the AMOC and helps illustrate the journey this water takes from the equatorial regions all the way to the North Atlantic.
Now let's get into what's actually changing the AMOC. Human-driven climate change is playing a central role here. One of the biggest disruptions comes from the melting of ice sheets and glaciers, particularly in Greenland. When this meltwater flows into the North Atlantic, it adds a large amount of fresh water, which reduces the salinity of the ocean in that region. This is a problem because lower salinity means lower density, and that means the water doesn't sink like it used to. That disrupts the overturning part of the AMOC. At the same time, global temperatures are rising, which weakens the temperature difference between the equator and the poles. That further slows down the circulation. The graph here represents a long-term climate simulation. It shows that Arctic sea ice melting acts as a trigger, reducing salt and heat flow into the North Atlantic. Eventually, although there might be a form of recovery, the system would be permanently altered, operating in a fundamentally different way. This points to the nonlinear nature of climate systems. Once pushed past a certain point, recovery isn't guaranteed.
Historically, we've already seen a measurable slowdown. Research suggests that the AMOC has weakened by about 15% since the 1950s. That may not sound like a lot, but for such a massive system, it's significant. Climate models predict that if greenhouse gas emissions stay high, the AMOC could continue declining and possibly collapse entirely within the next 100 years. This kind of tipping point, where a system moves to a new state and can't return, is a major concern in climate science. The visuals here show how a weakened AMOC would lead to drastic surface air temperature changes and shifts in precipitation around the globe. For example, some regions might experience extreme drought while others could see persistent flooding. The consequences wouldn't just be regional, they would be planetary.
Impacts of a weakening AMOC. The effects of a weakening AMOC are far-reaching. Europe would likely see significant cooling, especially in Western Europe, where the AMOC currently brings warm water and air. In North America, we'd see increased storm intensity, including more frequent and powerful hurricanes. There'd also be unpredictable shifts in rainfall and drought patterns. Marine ecosystems would be deeply affected also. Since many fish species depend on stable temperatures and nutrient flow patterns, their populations and migrations could be thrown off balance. This has a ripple effect across entire food chains and global fisheries. You can see in the visuals that the rate of oceanic species invasions and continental warming aren't uniform. Some places will be hit harder than others. This reflects how climate change interacts with geography and ecosystems in complex ways.
Let's now focus on specific real-world consequences. In Europe, colder winters could strain agriculture and energy systems. Crops that once thrived in temperate climates might struggle while heating demands would increase, putting pressure on energy grids. In the US, especially along the East Coast, Sea level rise driven by AMOC weakening is expected to cause more frequent flooding, including sunny day floods unrelated to storms. Marine biodiversity is also at risk. Changes in ocean currents and temperatures could collapse fisheries, especially in regions dependent on predictable seasonal upwellings. This threatens food security, particularly for communities relying heavily on seafood. These maps show the increase in flood frequency across the US and the agricultural stress in Europe. This isn't abstract science. It's already starting to unfold.
So, what can we actually do about this? First, we need to reduce greenhouse gas emissions to slow down global warming. This means phasing out fossil fuels, implementing carbon pricing, and transitioning to renewable energy sources like wind, solar, and hydro. Second, we should invest in renewables and sustainable agriculture to reduce land use emissions and prevent further deforestation, which also contributes to carbon buildup. And finally, we need to closely monitor AMOC changes. Satellite data and ocean buoys allow scientists to track changes in salinity, temperature, and ocean current velocity in near real time. The visuals here include diagrams of the carbon cycle and maps of ocean temperature trends linked to AMOC. These tools help us understand what's happening and prepare for what's next. The time to act isn't in the future, it's now.
To conclude, we've compiled a comprehensive bibliography which includes peer-reviewed research, climate model datasets, and reports from institutions like the IPCC and NOAA. These sources guided our research to ensure that everything we've shared is backed by credible science, because this is real and this is now. Thank you for your attention.